and I will record myself just in case. Okay. So, so the idea is I will first introduce the development process of classical singular integrals all the way up to the Calderon-Sigmund class of singular integrals. In just a very brief introduction, and then we will do the same through the looking glass to the Gaussian singular integrals, and then we will discuss what I call general and general alternative Gaussian singular integrals. And finally, we will mention the properties, the LP properties, and the weak one properties with respect to the Gaussian measure and also the Gaussian Lebesgue space, variable Lebesgue space. Okay. Well, singular integrals are one of the most important operators in classical harmonic analysis, and I want to try to justify uh, why is that? I mean, and why this is a natural type of question. When you go to a measure theory course, one very important inequality is Young's convolution inequality that says that if you have a P between 1 and infinity, LP, F in LP, and G in L1, the convolution is in LP. Right? That, well, is just this. So therefore, if as long as you fix a function G in L1, you define a linear transformation through the convolution, right? And is LP bounded thanks to the Young's convolution inequality. So of course the question is what happens if G is not in L1? Well, can you still prove that, say, a convolution operator defined like that is in LP? And the answer is probably depends of the properties of G. Of course, and this is what I mentioned already, why do you want to do that? I mean, why is that needed? I mean, why get life so complicated, right? Well, here is a nice and classical example. For instance, singular integrals appears in the proof of the LP convergence of Fourier series. Why? Well, uh, um, if you have a function in L1 of the torus, or if you prefer 0, 2 pi or negative pi pi, you the Fourier idea was, well, you can expand your function with the trigonometric basis, where the ck's in this complex notation are the internal product of the function against the conjugated. Right? So it was known, and for instance, this is what appears in when you teach a course in partial differential equations, that you need if you want to prove pointwise convergence, you need to restrict your functions a very small set. For instance, the first analytic proof of that was Dirichlet, and he proved that if the function is continuous, monotone, then you can have it. In the standard books these days, I mean, you ask that function is continuous with I mean, piecewise continuous with piecewise continuous derivative. So that with that you can prove pointwise convergence And well, of course, in the point that there is discontinuity, well, then it will converge to the average of the jump. But if you want to go beyond that, then you need to get some different notion of convergence, right? So of course we need to prove, for instance, we are talking about a series, so yes, you need to consider partial sum of the series and try to see in some sense what that converges. So the natural extension was to see if converging LP. The case P equal 2 was actually the first one, and what you do is you prove that the trigonometric system is orthogonal and complete in L2, and then you apply the Hilbert space theory, with that give you the convergence immediately. But I mean, if you say it like that, actually it's the other way around. The whole Hilbert space theory developed from this problem, right? And of course, if P is not equal to 2, it's a much harder problem because, yes, you are changing from Hilbert space to Banach space. And then there is where the harmonic analysis, the tools of harmonic analysis get into play. So a very beautiful representation, which has been a paradigmatic one, is that, well, the partial sum can be written as an integral representation. Just you take, in order to get that, you take here, oh, come on. You replace CK by its definition, and then you interchange the integral with the sum. There is no problem because it's a finite sum, and then doing some nice, clever computation, then you can get to this thing. And another clever computation, you see that this kernel is what is called the Dirichlet kernel, can be written in this form. When you see this immediately, see that, I mean, this kernel oscillates, has certain localization property, but is positive and negative, and that is probably one of the worst disadvantage of that. So fortunately or unfortunately, the Dirichlet kernel do not have nice properties, and that is what makes the problem hard. It can be proved, and it's an if and only if, that the problem of convergence of the partial sum to F in LP is equivalent. And the equivalence, in one way, you need to use that the trigonometric polynomials are dense in LP, and in the other side, you need to use the famous Banach-Steinhaus theorem to prove that the partial sums happens to be LP-bounded operators. And this is what you do. You prove this. Since the Dirichlet kernel has bad properties, you use this little trick that average the partial sum with the previous partial sum, and then what you get is Sn minus the two final terms. And it can be proved that, well, then this Sn has that the kernel is the average of the Dirichlet kernel, and then it can be, you can write this in this form, and then you can split, sorry, this is a minus here, you can split this in these two parts. And this is exactly the point in which, sorry, no, this is not a minus. you can prove that this is equal to this, and now you use just the the trigonometric identity to write it this sign nt. Well, you need to change. Oh, you have to put the convolution in the other side. I'm sorry, and then you can write it like this. And this is the important part, because yes, here you can see that you are convoluting this function f of t cosine nt and this function f of t sine of nt with 1 over 2 tangent of 1/2 x, right? Which happens to be not integral, right? That's the point. And so it's exactly there that you need to study this operation. And this operation is what is called the conjugate function. Of course, the way to understand this, I mean, this blows up at when t is equal to x. You need to understand that using what is called the principal value. That is, you take t less than epsilon, bigger than epsilon, and less than t. But it's completely symmetric, and then you are integrating very carefully. This makes perfect sense because you are away from the singularity, and then you take epsilon tending to 0. This is the way to make sense out of this integral. And then, well, if you are able to prove that this guy happens to be LP, well, then well, this is bounded by 1 over p. Then you take the norm of this, and that then will be bounded by the norm of f times cosine, the norm LP, but cosine is less than 1. That is controlled by the norm of FP, or the norm of f, and similarly here. So the whole problem of the convergence in LP for the partial sum of the trigonometry of the Fourier series is based on the fact that you can prove the LP convergence of this guy. Once you have that, then you immediately get this, and then an easy computation give you that these two guys are very close, and then you get the partial sums are bounded, and then you have then the LP convergence. So this is a case that, you know, is a very classical one in which you see that you need to understand this. So most of the problem then is to make sense out of this and prove the LP boundedness of this operator. The original proof is from 1920s. It was given by Marcel Ries using complex methods, because there is another way to motivate the conjugated function using Cauchy-Riemann equations. I mean, the very complex root. Since the near 0, 1 over 2 tangent of x over 2 is like 1 over x, of course, there is a twin brother of this transformation in the real line, non-periodic case, that is what is called the Hilbert transform, right? So you just change.
Wilfredo, in equation 7, you want x minus t bigger than epsilon, right? Or you want to put the convolution in the f or something.
X minus t bigger than epsilon, yes.
Yeah. Mm-hmm.
Sorry. Is that I changed the reason to the last moment I changed where the convolution was, because I have it. I wanted to make it look close to this one, but I forgot to do that. You are completely right. That was also the mistake in Misha's poster in the conference back in Caracas, by the way. Okay, so then from the conjugated function, you get the Hilbert transform in R. And then if you go to RD, well, you get the Ries transform. That looks like this one. The Ries transform, which is in honor of Marcel Ries. When you take Fourier transform of the Ries transform, you get that is a multiplier, and this is the multiplier term. And from there you can see that then the Ries transform is the partial derivative with respect to xj. The j Ries transform is the partial derivative with respect to the negative Laplacian, the inverse of the square root of the negative Laplacian. Okay. And then, and from there, then you go a little higher. Then you say, well, I can take convolutions with anything of this form where this guy is defining the unit sphere in RD, the SD minus 1, that the integral over the surface is equal to 0. Okay, so for all of these guys, and for instance, you can say, well, why do you want to go to the dimension? For instance, well, yeah, this derivative, for instance, in physics is important because, for instance, the second derivative of the Newtonian Laplacian happens to be also a singular integral. So it appears in a lot of places. Then finally, I mean, and all of this, of course, once you are out of the torus, you need to have different methods of the complex method that are used by Marcel Ries. So Calderon and Alberto Calderon and Anthony Sigmund developed what is called the real method, and the famous Calderon-Sigmund decomposition. And with that, you can prove that all these operators happens to be LP bounded for P bigger than 1, and in the case of P equal to 1, are weak 1, what is called weak 1, 1. And finally, you could say you can go even beyond convolution, and then you have a class of Calderon-Sigmund operators in which the Calderon-Sigmund kernel is a kernel, not necessarily a convolution, that satisfies these two estimates. And then you can prove that the principal value of something like this is LP bounded. If, for instance, you start with a continuous extension in L2. And these are this is the real method by Calderon and Sigmund. Okay, so let's go through the looking glass to the Gaussian case. And in this case, instead of the Laplacian, the natural operator there is what is called the Ornstein-Uhlenbeck operator. There is good news and bad news. The good news is that, I mean, the Laplacian was self-adjoining, formally self-adjoining L2, well, the Ornstein-Uhlenbeck is formally self-adjoining L2 of the Gaussian measure. A good news, though, is that the Hermite polynomials are eigenfunctions corresponding to this eigenvalue. So this differential operator has a point spectrum only, and that's very good. So, as I already said, is self-adjoint, and so then this is the symmetric Laplacian in the Gaussian context. The bad news, though, is that if you consider the derivatives, what we call the Gaussian derivatives, well, this in harmonic analysis there is always a 2 pi fooling around that you don't know where to put it. Well, in Gaussian case is the 2 or a square root of 2. So normalizing, if you consider basically the derivative, well, the derivative is not symmetric nor antisymmetric. In the case of, in the Lebesgue case, the derivative is antisymmetric, right? It's just the integration by part trick, right? Here is not symmetric, not antisymmetric, and the formal L2 adjoint is this guy. This in quantum mechanics, and I don't know much about it, but this is the derivative is called the annihilator operator. Well, at least you can see that in the polynomial because reduce the degree in 1. And this is the creation operator because, yes, you are multiplying by x. You increase the degree. Okay, then you can write the minus the Orten-Uhlenbeck operator as the sum in each variable of the derivative of the adjoint times the derivative, right? And this is one of the source of a problem, right? So going back to what I said about the Riesz transform, and this is where I started working back when I was a graduate student, the Riesz transform happens to be the derivative of the inverse of the square root of negative Laplacian. And then from there, that is a very key idea. Then you say, well, if everything is correct, the Riesz transform in this case, you take negative the Orten-Uhlenbeck, the inverse of the square root of the Orten-Uhlenbeck operator, and take the Gaussian derivative. Right? So that is, so this guy is what is called the Gaussian Riesz potential of order 1/2. And this guy, as I said, is the Gaussian partial derivative with respect to AI. Okay. So one thing that we are lucky here is that we can see what is the meaning of this. Well, the meaning of this, we can just go over the Hermite operators and see what is going on. So yes, then because of the action of the functional calculus here, you can see that the action of the Riesz transform in the Hermite polynomial of degree nu will be 1 square root of 2 over the the norm or the modulus of nu j, the Hermite polynomial of degree nu minus ej. So you subtract in the corresponding order 1, right? And it can be proved that the Riesz transform can be written in this form, and this is the kernel, which is not, it doesn't look like a user-friendly kernel, and it's not actually, but it is what it is, right? I want to make a notice of this term here. I mean, you can see that it's exactly what is in the denominator, in the exponent here of the exponential, and that will have some consequence on this term. So yes, we can get an integral representation of this guy, and this was considered in 1969 by Benjamin Mackenhoff, a student of Elias Stang, that they started in 1966. All these things about harmonic analysis with respect to orthogonal polynomial expansions. They did the first case that is a long paper in the transaction using the Gegenbauer polynomial, and they did, at least in one dimension, basically all the theory that you would like. So in one dimension, using a technique based on what is called the Nathanson lemma, Mackenhoff proved the LP continuity of this transformation. And in 1984, Paul-André Meyer uh, um establish the LP continuity in D dimensions using probabilistic tools, the Burkholder-Gandhi inequality, among other things. Um, and this is precisely what the Dan Struck was aware. Of course, in probability, they don't really, at least at that time, they were not really considering that explicitly as a singular integral. And so this is what they prove. Okay, Gandhi obtained another proof of this inequality using, again, Brownian motion and a notion of what he called background radiation in 1988. And Gilles Pissier got also another proof using the method of rotation and transference method. So, as I usually say, everybody have proved this, including me, right? So part of my thesis was prove this using real analysis methods, right? What nowadays are called kernel methods. So it's just looking at the kernel and chopping down this integral in several pieces, trying to prove it. Or as Gandhi once said, well, that's the macho way. Okay. Of course, there are big difference in this case respect to the constant. Sorry, there is another mistake here. There is a constant here. That these are not construction. There are missing constant here. That's a typo. Sorry about that. And this is one of the problems that the proof used the Paul-André Meyer, Gandhi, and even Pissier, the constant that appears in the boundedness are independent of dimension because are basically using probability. When you try to do that using studying the kernel directly, independent of dimension is a long shot. And okay, of course, in harmonic analysis there is an area that is very close to probability, which is Littlewood-Paley-Stein theory. And using that, in 1994, Christian Gutierrez got a proof with constant independent of dimension using the analog of the G functions in this context. And in 1996, Sonsoles Perez and Fernando Soria, Sonsoles Perez was a PhD student of Fernando Soria, got again an alternative real analysis proof studying the kernel, but again the constant depends on dimension. But nowadays I will say that Sonsoles Perez method using kernel techniques is probably the best written. It's not easy anyway. None of the proofs are easy, but Sonsoles proof it has a nice route that has been followed by a lot of people afterwards. So with respect to P equal 1, Mackenhop proved already in the same paper that is the Hilbert transform is weak 1. That means this, that the measure, the Gaussian measure of the point in which the Hilbert transform is bigger than lambda is controlled by 1 over lambda, the norm of F1. That's the weak 1 inequality. Roberto Escoto, was also a PhD student that came after me, right after me with Jim Fabe, got the weak one for the Riesz transform in general. Um, and the method that he used was based on a method developed by Peter Sjögren. Um, so he proved this uh, in his PhD thesis. And then Sonsoles also obtained an alternative proof for this using completely different methods, more geometric method. Okay, when you go to higher order, well, again, I say that the motivation for the Riesz transform was this one. So if you want higher order, well, you need to take a higher order Riesz potential and a higher order derivative. So in that case, yes, you take a derivative of order beta and take the Riesz potential of order modulus of beta over 2. Again, you can see the action over the Hermite polynomials explicitly. And yes, if this is order beta, since you are taking beta derivatives, well, then the polynomial will go down in order exactly that, and then you have this term. And this representation, we studied these representations, I will talk about that later, give a nice proof of this. Okay, so the kernel, remember I said for the Riesz transform, you get this guy down here. And you can split this in two pieces, the denominator, this one, and you can see that this is the derivative of this guy once. If you take the d plus 1 over 2 this way, then you get exactly the derivative of this down here. And then, yes, what I realized back then is that, yes, when you try to do the kernel, this is the kernel that you get, in which you are taking beta derivatives of the exponential. And then, well, what appears, using precisely what is called the Rodriguez formula for Hermite polynomial, is that in the kernel appears the Hermite polynomial of order beta. So this is the kernel that you have to deal with in chopping down, and yes, it can be proved that LP boundedness of this guy. So for higher order Riesz transform, I gave in my thesis the first analytic proof. PCR extended his method of the Riesz transform to the higher order, but his method only worked for beta, the order of beta odd. For even, it doesn't work. But as I said, the advantage of PCR method was that the constant was independent of dimension. And then in 1996, Gutierrez, Segovia, and Torrea extended what Gutierrez had done for the Riesz transform, and were able to prove this again with constant independent of dimension using Littlewood-Paley-Stein theory. Okay, and then in 2000, Sonsoles, Perez, and Soria obtained an analytic proof with constant dependent of dimension with the same technique that they have done for the maximal function of the Ornstein-Uhlenbeck. Okay, and then in 2001, Liliana Forzani, Roberto Scotto, and myself obtained a very simple proof based on exactly this explicit representation. From here, what you can see is that basically this guy, if you compare this guy with an iteration of Riesz transform, uh, iterated this exactly this order. So you compare this guy with the iteration of Riesz transform order one more than once, right? Between them, there is what is called a Meyer's multiplier. So with that, we got a proof that is, probably a page or something like that, no more than that, of the of the LP continuity with constant independent on dimension. For instance, Gutierrez, Segovia, and Torrea is a paper that is almost 40 pages to prove it. Of course, they need to develop the Littlewood-Paley-Stein theory, the higher order G functions, in order to be able to handle that. But I remember I was in, well, Cristina has been in Escorial. Uh, I mentioned to Segovia about our alternative proof that was a very short proof, and Jose Luis Torrea got very upset with me, and he didn't want to accept that that was possible to prove it directly using Meyer's multiplier. Well, then immediately you ask, well, what happened with the weak one boundedness of the Riesz transform, higher order Riesz transform? And that is a huge surprise. Because in 1998, Liliana Forzani and Roberto Scotto proved that, yes, the order 2 are weak 1, but order bigger than 3, even in one dimension, are not weak 1, which is completely out of the chart. I mean, that is not expected at all. And then in 1999, Garcia Cuerva, Pepe Garcia Cuerva, Maucheri, Sjogren, and Torrea obtained the same result for D equal bigger than 1. Even some think that there are some holes in the proof, but and then finally, in Sonsoles also gave an alternative proof for the kernel of order 2, and the impossibility for kernel with order bigger than 2. Okay, now, well, I am almost done. Okay, but I need to rush. So remember, the higher order Riesz transform, you have here the Hermite polynomial of the corresponding order, right? So already in my thesis, we say, well, if instead of this guy you have, well, it's trivial. If you have a polynomial, well, the Hermite polynomial is an algebraic basis of the polynomials. You can do that, and even you can extend it to functions that has that grows no faster than polynomial. That was we didn't do much of the detail in that case. I was already exhausted with the thesis, but there was this hint that because I mean, at that point, what we want is to characterize: is there a family of singular integrals in the Gaussian case, as there is the Calderon-Sigmund family in the classical case? So the first hint was given by me, and then Sonsones Perez introduced a much larger class following the same idea. That is, you consider a function that has integral 0, a C1 function, and such that the function and the gradient of the function do not grow faster than this bound, which is exactly, I mean, remember, we are integrating against the Gaussian measure, and this is telling you that you will not cancel the action of the Gaussian measure. And then, well, if you define the same idea as before, but instead of having here the 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 Hermite polynomial, you have this function. Can you prove LP boundedness? And the answer is yes. The answer is yes. So you need to deal with this kernel and it's possible. And nowadays the Sonsoles proof is now the kind of the standard, right? As I said, I mean, this condition 38, I already have some hints about that when the function f has at most polynomial growth. Okay, and of course, if you take f equal to the Hermite polynomial, yes, you are back to the higher order Ristrand form. So these are, so in 2001, Sonsoles Perez proved this. Of course, we already know that the weak 1-1 are not good in general, so she also proved under certain condition on F that the TF is not weak 1-1. Well, you know, there has been this development of Lebesgue variable spaces where the exponent is not a fixed but a function. So the function has to have certain regularity. And in 2017, Stefania Dalmaso and Roberto Scotto proved the LP variable boundedness of these guys. And of course, they were forced to introduce a regularity condition over P that is not of the standard ones in the theory, in the Lebesgue case, that fit exactly for the Gaussian case. The scheme, though, of their proof was based on the Sonsoles Perez proof of this inequality. All this proof, it started, and I remember it started in my thesis that, you know, you have to treat your kernel carefully enough, and you split in nowadays term, you split in two parts, right? Local and global part. The local part is near zero, so you take a bounded region there, and of course in the bounded region you can control the Gaussian measure. So the Gaussian measure is controlled, and then, well, is essentially a multiple of the Lebesgue measure. So morally speaking, in that region, what you see is a classical singular integral. And so then that is supposed the hard part. In this case, it's not hard, because then in the local part, you just bound by as you know from the classical theory. The whole problem is the global part. It's a positive operator, but it's always a mess to try to control it in any of the proof. Now, let me go back and say that all this started saying, okay, we have that the Ornstein-Uhlenbeck operator, can be written in this form. But this is not symmetric. So a natural question is, what happens if you change the order here, right? So an incredible turn of the events was given by Hugo Aymar, uh, um, Hugo Aymar, Liliana Forzani, and Scotto, that proved that changing the order, right, and considering the operator represented with the opposite order, that's what we call L bar, and taking not the derivative but the adjoint of the derivative, you get other Riesz transforms. That I call it alternative Riesz transform. Okay, and uh, and then of course the higher order will be the same. Well, taking the higher order, the adjoint higher order derivative, and then the Riesz transform of order, the corresponding order, right? Okay, so in that case, this operator happens to be a lot nicer. You can get the kernel of it too, is here. See, we are still talking about higher order Riesz transform, and you can see that you have this guy here. And then they prove that the LP bounded, and yes, this can be done, for instance, using Paul Andre Meyer multiplier, the idea that Liliana, Roberto, and myself did for the usual case. But the amazing thing is that these alternative Riesz transform are always weak 1-1. And so this works good. Then, of course, the natural step that we did recently is that, well, there should be some alternative generalized Riesz transform that is the same idea, singular integral. That is, if you change this guy by f, what can you say? Well, yes, you can. If f have the same conditions as before, f is equal, the integral of f is 0, and f and the gradient of f do not grow faster than this guy, you can prove that what we call the generalized alternative Gaussian integrals are LP bounded. We proved that, like I think there was 2 years ago. We also proved that they are weak 1-1 with respect to the Gaussian measure. And more recently, and that is a paper that has been has a very bad luck. Well, I will talk about that. I still have 5 minutes. Okay, so we follow Dalmaso and Scotto approach. We prove first that the maximal function of the Orsen-Uhlenbeck semigroup is LP bounded with LP variable. But unfortunately, in the classical case, the Orsen-Uhlenbeck semigroup is a semigroup of construction. You cannot get that from this method, unfortunately, and we don't know, for instance, if it's not contractive, much less you can say anything about hypercontractive. And then we prove, following also Dalmaso and Scotto, we prove the LP variable alternative singular integral with the same condition of regularity introduced by Dalmaso and Scotto for the exponent P. Recently, I have we sent it to a journal, and it was rejected because it has an overlap of 17% with Dalmaso and Scotto. Of course, the introduction and all the framework for the LP variable Lebesgue spaces is the same. That's the 17%. But the editor didn't move. I mean, it is an misuse and abuse of, of, of the of the software. But we have not been able to publish this last result. The previous result, this was published already in 2020, but the other one is still going around. Okay, so these are the reference, so it's perfect. So this is the famous Aymar, Forsani, and Scotto that gave this different uh, um, Gaussian wrist transform. This is the Scotto and Dalmaso paper in the invariable Lebesgue spaces. And this is the paper by Scotto, Fapes, and Gutierrez. That's a long, I don't want to talk about it, but about the weak 1-1 of the first order wrist. And this is the original paper by Mackenhoff. That Mackenhoff is an incredible mathematician. He did not only the Hermite case, but also the Laguerre case in the same paper, which is out of this world. And so this is the paper of the alternative one. Is in this journal of stochastic analysis. This is, well, submitted for publication, I don't know when, again. And this is the paper by Sonsoles that is a framework. The rest is and if you want to learn more, well, thank you for your attention. If you want to learn more, here is a book. Okay.
Thank you, Wilfredo, for a very, very nice talk. Let's see, do we have questions? I have questions, but somebody else wants to. So, can I ask you, Wilfredo?
Yes.
I'm sure somebody has done it. So does it? Has somebody studied like weighted inequalities for the? Do you have some Gaussian AP or classes or something like that? Or
there are. I mean, it has been very complicated. I mean, but I know that Paul Arbure and Scotto, and I think Beatriz Viviani has some computations about weights, but it's not nice, and it's not a nice theory though. I mean, it's not.
And how about sparse domination of some sort? Never heard. I mean, I'm pretty sure the crowd in Argentina is thinking on, but I don't know. Maybe it's yeah. Maybe it's not the right thing to. I mean.
Yeah, I don't know.
Yeah. Well.
Yeah. So.
Oh. Roberto Scotto was here.
Oh.
Roberto, where are you?
Hello.
Hi.
I'm in Santa Fe.
You're in Santa Fe.
Yes.
Very good. So Santa Fe, Argentina, for those of you who...
Yes, you're right. Because
not Santa Fe, New Mexico.
Yes, you're right. No, not there.
Santa Fe is the capital, actually, in New Mexico, no? But
No, okay.
And Edward Nava is one of my collaborators. He's in Venezuela.
and Eduardo Navas. Hi, hola. Welcome. So where are you, Edward? Eduardo, ¿dónde estás?
Venezuela,
¿Pero dónde?
Falcón.
En Falcón, eh? I'm not asking just, I mean, it's not, okay. En Coro.
No, punto fijo.
Punto fijo, okay. Very well. Well, any questions for, any further questions? Ebner is here too.
Oh, yeah.
Oh my gosh, Ebner. Where are you? No te oímos. We don't hear.
It's in Ecuador.
In Ecuador, so we had the crowd from Latin America.
Venezuelan diaspora.
Very good. Well,
I put my T-shirt from the Universidad Central de Venezuela. ¿Sí?
Wow.
UCB. Very good. So let's give Wilfredo another round of applause, and thank you very, very much for a great talk. There is no analysis seminar today. This was it. We have an analysis seminar next week on Friday, and it's going to be Joe Lakey. Is it Joe Lakey?
Tomorrow, you mean? Or
No seminar tomorrow.
okay.
Next week, only on Friday, no colloquium. And if the crowd from Latin America wants to hang out a little bit, we can chat for a little while.
Bye. Thank you for your attention.
No te vayas, Wilfredo.
Okay.
I know my advisor in Denver was Guatemalan. I don't know if that's.
Who was him?
Alvaro Arias was his name.
Alvaro Arias.
Arias.
No? Okay. Yeah, big continent.
Yes, indeed.
Well, goodbye.
Bye.
Bye. Bye, Lihan.
Thank you, Professor. See you soon, I hope.
Take care. Probably see you. When is the analysis, the EMS?
In October 23 and 24. Okay. Hay como 3 sesiones de Harmonic Analysis.
Ok, bye.
Bueno, podemos hablar en español.
Los latinos.
Los latinos, muestren sus caras si tienen band suficiente. Ahí estamos. Bueno, bienvenidos a Albuquerque.
¿Se hablaste, Wilfredo?
Gracias.
¿Cómo?
¿Ya diste la charla o empieza ahora?
No, ya la dio. Pero la estamos grabando. Ya, pero la grabamos. Así, déjame opción, pero se las mando luego. O se la mando a Wilfredo y Wilfredo se las manda. Ustedes acaban de entrar pensando que la charla era ahora.
Sí.
Oh,
Los tres.
Estaban con el horario de Wilfredo, probablemente, ¿no?
Yo me iba a conectar a las 4:30, pero cuando vuelvo a ver el mensaje, decía 5:30 Chicago, entonces le dije a Eduardo, no, falta 1 hora todavía.
A mí me pasó lo mismo.
Ay, creo que fue mi culpa.
Porque, claro, decía 5:30 y a Argentina hay 2 horas adelantadas.
Ay.
Sí. Claro, es que esto es Mountain Time, era la hora de, bueno, no sé qué hora diste tú, Wilfredo.
No, yo dije 4:30 Mountain Time.
Pero era 3:30 Mountain Time.
Bueno, me lo perdí.
Pero bueno, Wilfredo les manda.
Bueno, perfecto.
Pero Roberto,
entonces.
es más, te mandas más transparencia, pero me mandas tus transparencias, porque Roberto dio una...
Sí, te mando la charla.
Okay.
Wilfredo les mandó la hora equivocada, acaba de terminar.
Sí.
A ver, Jorge, ¿de dónde viene?
Jorge viene de Barquisimeto.
De Venezuela.
Bueno, ajá.
Barquisimeto.
De Barquisimeto.
Ebner también es de Barquisimeto. Bueno, Edward también.
No,
También.
sí.
Pero ¿quién es el que está en punto fijo en Falcón?
Yo.
Tú estás en Falcón. Y
Ajá.
Ebner, ¿tú dónde estás?
Yo estoy en Guayaquil.
En Ecuador, dijiste, en Guayaquil,
Sí.
ok. Pero, ok.
Jorge está en Barquisimeto
En
todavía.
Barquisimeto, ya.
Sí.
Bueno, Wilfredo les mandará la grabación cuando Zoom me la mande a mí. Oye, todavía está grabando. Y si yo pensé que la había parado. Espera.
Sí.
Ah, es que tú estás grabando, Wilfredo. No, ¿cómo es la cosa?